All right, so what are we after with the Ka for acetic acid? We know that acetic acid is, that in aqueous solution, and it's going to, the simplified version, do this, H3O2 minus. So the K that we're after is equal to that and this over this. There we go. Now, I think I mentioned this before. The way we're going to do it is we're going to titrate this acid with base. We're going to add hydroxyls to the solution in increments. So we know how much base we're adding each time. That produces water and drives the reaction this way. Okay. So what we should get, you're going to have a list, you're going to have a data table of pH and added hydroxyl. All right, so you're going to have actually not concentration, it's going to be milliliters of added base. So you're going to start off with a certain amount of acid. And let's go to the method. Materials. 0.1 molar acetic acid and 0.1 molar sodium hydroxide. So you're going to have so many milliliters of, it looks like 25 milliliters. Yeah. You're going to start off, you're going to have 25 milliliters of the acid measured very accurately using a volumetric pipette. And the pH is going to be something like 3 point something something, probably. And this is with no base added. Then you're going to add base in increments. And the increments are going to change. And the method tells you how much to add each time. So we'll just cookbook that part of it. Let's see. Until you reach a certain pH, you add so much. And when you get this, so many milliliters, and this is total milliliters added each time, right? It's not the increments that you're recording here. It's the total amount that you've added up to that point. And what's the pH response? Then when we, total amount of added base in milliliters. And then the pH is over here. And we're going to get, draw a curve that looks something like this. Right? And then pH values over here. Okay. So, first thing we want to do with that data is find out where is the equivalence point. How many milliliters of base was required to get to this point right here, the point of inflection from concave up to concave down. It's right midway on this straight part. So you could do it, once you draw your graph, you can do it by hand, right? So you just find out where it starts to curve and say, all right, there, and where it starts to curve here, and then there, and then just take the halfway point, and then you drop a vertical down to here. And that's your equivalence milliliters of base. And we know from Henderson-Hasselbalch, equals log of the C2H3O2 over HC2H3O2. We know that if these are equal, that's equal to 1, and that term goes to 0. So what we want is the equal amount of this to this. And that occurs at half equivalence. So at half equivalence, right here, is the middle of your buffer zone, plus it's the pH that's equal to the pKa. So then you just follow this across here, and that's your pKa. And then, of course, you know how to calculate Ka from pKa. It's the anti-log of the negative power. Okay, so that's the procedure in a nutshell. Let's see. Let's go back to discussion questions. Let's see, did I include discussion questions? Here it is. Yeah, discussion questions. Unless you have questions about this procedure, it looks pretty straightforward. And this lab, by the way, requires a formal report. Okay, discussion questions. So the first one is definitions. Okay. A, B, C, and D. Definition, what is the equivalence point? No idea. That's when acid equals base, which means that we've used up enough base to neutralize all the acid, and all we have left then is the net equation. When the moles of acid equals the moles of base. Let's do it that way. Moles of acid equals the moles of base. And when we say that, we don't mean the molecular base and the molecular acid, because they can have, this could be polyprotic, or this could be polybasic, like calcium hydroxide. What we mean is moles of hydrogen ions, hydroxyl ions. Okay. That's the equivalence point. What is the end point? That's close, close to the equivalence point as determined by indicator color change. That's this. We try to get this as close as possible to the equivalence point, but it's usually not possible. And then we know what the Ka is. That is the acid ionization. Sometimes they say dissociation. Acid ionization constant. And pKa is the negative log of the Ka. Okay. All right. Let's take a look at number 2. If 23.9 milliliters of sodium hydroxide is required to titrate 25 milliliters of 0.105 acetic acid solution, what's the concentration of the sodium hydroxide? All right. Let's do the stoichiometry first. You've got sodium hydroxide reacting with acetic acid. And that produces water plus sodium acetate. Okay, that's the stoichiometry. So you can always go back to the balanced equation, and that way, if you have a polyprotic acid, then you can work out the in the equivalence point from that. If you're in a hurry, then if you have one hydroxyl and one hydrogen, then you can say the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. That's if you have the same number, if it's a 1-to-1, hydroxyl and hydrogen. If it's not, then you can calculate the normality of the acid. And that takes the variations of polyprotic acids out of the equation. This accounts for it. Right. So if this is 1 molar and that's 1 molar, then in this case, that'd be 1 normal and 1 normal. But if this were sulfuric acid and you had 2 of those there, then this would be half the value of that one. Right. But in our case, we can use this one because 1 hydroxyl, 1 acid. And 23.9 milliliters of sodium hydroxide. So on this side, and this is our unknown, 23.9 milliliters. And this is molarity of the acid is 0.105, 0.105 molar, times the volume that we added was 25 milliliters. There we go. Then we can solve for that unknown. So the molarity of the base is going to be 0.105 times 25 divided by 23.9, which is 0.3 significant figures, 110 molar. Okay. Now, if you don't feel comfortable with normality, you can just write out the balanced equation and then do the stoichiometry from the equation, and it works fine. Okay, let's see. Number 3. In the titration of a weak acid, the midpoint of the buffer zone corresponds to a pH value of 6.1. Okay, midpoint of the buffer. That's the point we're looking for to determine the pKa. So if the pH at that point is 6.1, that means the pKa for that acid is 6.1. That's the pKa. What's the Ka? Well, the Ka would be, since this is equal to the negative log of the Ka, then we move the negative over here, and that becomes the power of 10. 10 to the minus 6.1 is the Ka. And that's, let's see. Um, only one decimal. One decimal. So it'd have to be 8 times 10 to the minus 7 would be the Ka. Right? Significant figures here, decimals there. So 1 and 1. All right. And then we have some pre-lab questions. That'll just get you warmed up. Okay, first one. Okay. Write the balanced molecular equation for the titration of acetic acid and sodium hydroxide. Oh, we already did that. Acetic acid plus sodium hydroxide. And this is what's going on as you're adding sodium hydroxide to the solution. Let's see, we'll get water, of course, and then we'll get a soluble citrate, C2H3O2, sodium citrate. That's the balanced equation. That's the molecular equation. The Ka of formic acid is 1.8 times 10 to the minus 4. So Ka of, let's see, formic acid. Oops. Yeah, that's right. There, that's formic acid. So that would be Ka of CH2O2 is equal to what? 1.8 times 10 to the minus 4. Okay. And the Ka of, let's see, just to be clear, formic acid. And the other one is lactic acid. I don't remember lactic. I should, but I don't remember lactic acid. I think it's a 3-carbon lactate. 1.4 times 10 to the minus 4. 1.4 times 10 to the minus 4. Okay. Which acid is stronger? Well, when you're looking at Kas, the larger Ka is the stronger acid. Okay. What is the pKa of each acid? In that case, you just need the negative log of each one. 1.8 exponent minus 4. Make the log, change the sign. So that's 2 significant figures. That means we need 3.74 pKa. And then 1.4, same exponent. Log. So this is 3.85. Right? Okay, and that can tell you also the strength. The smaller pKa is the stronger acid. Oh, that's it. That's it for the discussion and the pre-lab questions. Okay, let's see if there are any. We're going to use an indicator. Our indicator is going to be phenolphthalein. And in basic solution, base is pink and acid is clear. So what you'll see is, as we're going to have our reaction vessel is going to be sitting on a magnetic stir with a magnetic stir bar inside, so you don't have to mix it. It's continuously stirring. Each time you add a drop of base to that acid solution, you're going to see it go pink and then disappear. So the microenvironment of that drop is going to be pink for a while because it's basic, and then as it is spread out, equilibrates and diluted, then it'll go acid. But as you add more base, it'll stay pink longer. And when you get really close, what you want for your endpoint is one drop you add is pink for a while, and then it just goes away. And the next drop you add, it goes pink, doesn't go away. That's your endpoint. And it's sometimes if you haven't done a lot of these with that particular chemistry, that particular acid-base reaction, then you could overshoot. Right? So we may have to do it twice. But that's what you're looking for. And of course, once you get to that, actually, we're not trying to, we do want to know the endpoint, and you'll make note, say your table says this, and you've added so many, then as you add the next amount, you'll want to note when that occurred, because that tells you where the midpoint of that steep part of the curve is. It's possible, since we're doing this titration using a pH meter, that you may overshoot, because we're not actually looking for the equivalence point to determine concentrations. We're looking for the values that will give us that curve. So what you may find is that it goes away here, and then it gets real pink and stays up here, and then you'll have to work your way in between. But you can just call your attention to when that happened. You can mark it on your table. And there was another thought I had. I was trying to. Maybe it'll come to me. These discussion questions, I want you to do on your own. And I'll point out this last one. When it says reproduce the mathematical derivation of Henderson-Hasselbalch, we did that in class. Right? So if you remember how to do it, great. If you don't, go look it up. Okay, that's all I have for today.